First, I want to welcome you all to this little workshop about our micro heating and cooling stage. These are the three systems we're going to be using today. The cooling stage itself. This is an image of that stage. You can see the stub here gives you a reference for the size. So this is a standard pin stub, about 12 millimeters in diameter. The stage itself is very flexible and easy to install. It slides onto the microscope stage as a sample holder would. Next, we're going to use our latest generation of micromanipulators. This is what we call an MM3E, the E-sensor encoders. This is the newest addition to our lineup of manipulators. It has positional encoders that allow you to drive the tooltip to predefined positions at a click of a button, which we'll see in a few minutes. And one other thing we want to demonstrate today in conjunction with the cooling and heating of samples is our EBIC and EBAC system, which we'll get to in a few moments. So briefly, the main specs for the cooling and heating stage, the temperature range is from minus 60 degrees Celsius to 125 degrees Celsius. The controller is capable of holding the temperature with a precision of about 0.01 degrees Celsius. The most important feature is this next one. The stage does not require external water cooling. And that, of course, makes its use very simple. There's no danger of water leaking into your microscope chamber. There's no vibrations. It just removes a whole chunk of hassle from using a cooling stage inside an SEM or a FIBSEM. And of course, we do include a software interface to drive the stage, and that interface allows one to execute temperature ramps or profiles, and we can record all the data that like power consumption and temperature and so on for documentation and also for analysis. Next to that, of course, the stage can be operated using the controller on the desktop, which is also an option for people who want to keep it simple. Okay, another close-up image of the stage with a sample mounted. Again, the pin stub gives you a reference of the size. And another important feature here is that the sample or the sample stubs are simply inserted into the substage, into a receptacle that doesn't require any tools. You just pop it in, it's a spring-loaded receptacle, you stick the stub in there, you pump it down, you're good to go. Let's talk about some applications for SEM observation. There are a lot of materials that prove to be difficult to image in SEM for various reasons. Maybe they're biological materials that need to be cooled, or pharmaceutical materials, chemical materials. And in this case, we're going to look at some polymer foils that charge heavily, even when platinum coated, and that prevents getting a very nice image of the substrate. In this case, these images were provided by our friends at the Zeiss Demo Lab in Oberkochen, and they tried various methods to image this very difficult sample, and these images are PT-coded samples, and the stage was biased to give you a beam deceleration. And the images are okay, they're getting there. However, they found that if they cool the sample down to minus 40 degrees Celsius, the images are much better. And we can actually make out a lot of the substructure here and identify certain contaminants that have found their way onto the sample. So I think this contrasts nicely the difference between room temperature imaging and imaging a polymer at low temperatures. I'm going to hand over to Andreas now, who's going to image a similar sample in our microscope.
Yeah, welcome to the live part of the workshop. You see now the installation. We have set up a micro heating cooling stage inside our Supra 40, along with 4 encoded micromanipulators. And on the stub, there are two samples now. One semiconductor device where we afterwards show the temperature dependency of PN junctions. And now we first start with a foil. We extract it from a lithium battery. It's not the separated foil, which Andrew just showed us. It's a foil we found between the shielding and a graphite layer. And we found out that it has also strong effect depending on the temperature and on the beam radiation. The effect might differ on different locations. So in the morning, we learned that some regions do not show a strong location, but the main goal is, of course, to show you the ease of use of the microheating and cooling stage. So we have here a software where you can see the current temperature. If you want to increase or decrease the temperature, you can just enter here the keys, and the temperature is set accordingly. Or you just enter the values you want to have, and the controller is increased or decreased according to the set temperature. If you want to see the temperature independence of the time, you can go to the graphics screen. So you see the temperature. The white line you see is the current temperature. It is now at minus 45 degrees Celsius. And the red line is the set temperature. So we just set the temperature to minus 50 degree, and now the temperature is approaching minus 50 degrees Celsius. In order to show you the temperature dependence of the foil, we have to increase the temperature, and we will set a temperature of about 90 degrees Celsius. And before we do that, we start the scanning. So this is an overview over the foil. So we zoom in here and start the temperature, 90 degrees Celsius plus. Now we have to make a slow scan, and now we already see the crackings here on the left-hand side. They are now going to be more defined, and with the higher the temperature is, the more cracks we will see, and the more distance will be between the individual grains. Yeah, if we have a look at the temperature now, you see now the white line is increasing quite quickly. We're already at 16, 17 degrees centigrade. And the power is displayed in addition. You can at any time save the current image, and all the data are stored as CSV file, and in addition you have a JPEG file of the current image. You can not only monitor the sample temperature, but also the stage temperature, which we measure in addition. So the stage temperature is now around 40 degrees centigrade, and you can monitor the power. This is to monitor, in principle, the control of the temperature. The temperature control is just a normal PID controller. You can set, if you want, all the values individually. Now we have, you see the power is now decreasing. That means the temperature is nearly reached. So if we go to sample temperature now, you see there's it's overshooting one time, and then it is soon approaching the 90 degree Celsius very, very quickly and stable. So yeah, let's. So this is not anymore interesting. We just monitor the thing. Yeah, you can see now it's not very clearly, but you can see the cracks are more and more can be seen more and more. And let's zoom in a location here. It takes also a little bit time until the temperature reaches the foil. The foil is a little bit insulating, but if you observe the different images before and after changing the temperature, you see a very clear change in the cracks. Now, before we go to the next sample, we again have to decrease the sample. We want to see the semiconductor device from a very low temperature to very high temperature. So we again go back to let's say minus 40 degrees centigrade and move afterwards to the next location. But first, Andrew will show you some more details on the next measurements.
So I want to briefly go back to the software and just show you a few more of its features. The one that we like the most, or one of the ones that we like a lot, is that we can define these temperature profiles where you have a table here indicating a starting time, which is always 0, and a temperature, and then you tell the software how many minutes you want to pass to get to a certain other set point, then maybe hold that temperature at a certain set point, then use a certain amount of time to go to the next set point, and so on. And this table is represented here in the form of a graph. So you get a visual representation of the sequence that you've programmed. These profiles can, of course, be stored and recalled for future use. You can run them in loops, in cycles, and so on. And it's very helpful to drive these kinds of experiments. And here, this is the result of the profile we just saw. The red line is the set point, and the white line represents the actual temperature that was measured. One could see that the system was powered on approximately here. And another feature here is that one, of course, control the graph settings. One can choose which information one wants to see, the temperature, the lower stage temperature that Andreas just mentioned, and of course the power consumption. And the data that one records can, of course, be saved using a predefined identifier, and it's saved as a CSV file, separated values, and that can be imported to any kind of spreadsheet software or the like. I want to briefly mention some FIPSEM applications. Of course, we don't have a FIPSEM here with us today, but I can show you some images of other experiments. In this case, again, provided by the folks at the Zeiss Demo Center in Oberkochen. But the examples are very, very interesting. So this image shows a gallium arsenide substrate. On the left, we see an image recorded at 30 degrees Celsius, and on the right at minus 60 degrees Celsius. And all that was done was to mill a box into the surface. And at warm temperatures, the material segregates and forms these bubbles, which is not what you're looking for if you're trying to make open up a window into your sample. So we see that going to very low temperatures reduces these artifacts to 0. And similarly, in cross-section on a CIGS sample, The same kind of artifacts are observed at warm temperatures here on the left, whereas these artifacts disappear when a sample is held at a negative temperature during milling. There are, of course, also other applications where using this kind of cooling is helpful. For instance, in preparing TEM lamella of unsensitive materials such as polymers, or trying to investigate pharmaceutical materials or biological substrates. There are a wide range of applications where cooling this substrate can be helpful. So we're going to move to the final segment of this short workshop. In this case, we're going to talk about some fault isolation applications. I had indicated in one of my first slides that we will be using EBIC. Before we go to that, I just want to briefly show you the geometry that we have today. This is the chamber of our Super 40, and we've mounted 4 MM3E micromanipulators to the roof. And it's just good to know, many of you maybe know this, but it's good to know that the 2 manipulators that are near the door are on the left side of the frame, and the 2 that are on the rear of the chamber are on the right side of the SEM frame. And I made this little illustration to demonstrate this. So when you're looking at the chamber from the top, you have to rotate everything 90 degrees, and that's what you see in the frame in the end, your 4 probes. That's just to keep in mind when you're installing your manipulators and you decide where you want them on the roof. It's good to understand how that will affect the direction in which they enter the frame from to get the geometry the way you want it. And then one slide about EBIC. I won't go into too much detail, but electron beam induced current is a method of visualizing buried structures, mostly p-n junctions. And this works by injecting electrons into the p-n junction, which creates electron hole pairs, which enables a current flow. And if there's a needle connected to the structure, then that current flow can be measured and visualized. And in this example here, the EBIC data, the red colored areas here, is superimposed on the secondary electron image so that one can identify certain structures and where they are in relation to other structures that are visible in the SEM image. And this is just a screen cap of the EBIC control interface, which we'll see in a few minutes. Just as an aside, one other thing that the EBIC system is capable of, amongst many more, is EBAC, electron beam absorbed current. And in this case, the electron beam current from the primary electrons that are induced into the sample are conducted along a conductive path. And if that path is connected to a needle that is connected to the amplifier, then that path will light up bright in the EBAC image, whereas other paths stay dark because they're not electrically conductive to this needle. And that again allows one to identify opens or shorts or other features inside a sample that may be buried a few layers down inside a semiconductor device, for instance. So I'll hand over to Andreas one more time, and he can show you this in real life and also demonstrate the temperature dependence.
Okay. Yeah, the temperature of -40 degrees has already been reached, and we are now switching to the next sample. Next sample, I have to select from the size stage point list, and the stage is automatically moved to the next sample. This is a typical operational amplifier, which we are going to contact with the encoded manipulators. Before we do that, we have to bring them from a parking to a restore operating position. Show you that first on the CCD camera. So we select here the restore command, and now the probes are automatically moved into an operating position one by one. So this is the first one, next one. we're using now 4 manipulators. Actually, we only need 2, but there were 4 inside, so just bring them all in. So you now 4 have already reached the operating position. Now we're waiting for the last one. And after all manipulators have moved to their position, we're now going to land with 2 of them. And this can be done by the macro editor. I've defined a macro before, but user is free to define any macro for any position, for any manipulator he wants to use. So just by starting this command, the probe is moved to the contacts, and I'm now only just some tens of micrometer above the sample and can land on the contacts. In addition to the probes, we have installed a live contact tester and an EVIC amplifier and a Keithley. The live contact tester is used to monitor the quality of the contacts. It's called the LCT live contact tester. If I switch it on, we should see the individual curves corresponding to the tips. So you see there's a little bit of shaking signal. This is from the electron beam. If I freeze the electron beam, we see the signal is becoming clear, and we see the diodes of the individual signals from the probes. Each probe is monitored 10 times per second. IV curve is applied and the current is measured. So we always see not only that the contact is established, but also which type of contact it is. This is important if you, for example, do probing on SRAM cells. You immediately know if it's NMOS or PMOS contact. Then we could, in principle, as this is only very fast, it's a fast measurement, giving only a quality. You can prove it also if you, for example, move now up with one manipulator. You see immediately that the signal is vanishing, going down again. The signal is done. So you can do this blindly without even using the electron beam. Now, if you have a Keithley, you could do a measurement with a Keithley. Here we have a Keithley connected to our software and a batch measurement that is measuring the individual diodes here by invoking the run command. The different types of measurements are performed that you have defined before. You can define 10 or more measurements just invoked by one command, and the results can be seen individually, and also they are stored in a separate Excel sheet for analysis afterwards. So now we go to the EBIC measurement. The EBIC measurement is done by routing a corresponding tip to the EBIC amplifier. In this case, we have routed tip number 1 coming from the top right-hand side to the EBIC amplifier. The others are left at ground. And you already see here in the video output, we can reduce the signal a little bit, that the EBIC amplifier is providing a signal where the EBIC amplifier is connected to the video input of the microscope, and we now select from the detectors the video input and have the EBIC signal here. Yeah, you see here white and black and gray parts. For EBIC, you have currents from PN junctions, and depending on how the probe tip is connected, you see currents or electrons flowing from the sample into the amplifier, or electrons flowing out of the amplifier to the sample. The white parts are electrons flowing to the amplifier, while the black parts are electrons flowing from the amplifier to the sample, and the gray parts are when no current is flowing. Now, what we want to see now is the temperature dependent effect. We can afterwards make a small analysis with the EBIC overlay tool, but let's first do the analysis using the temperature control. And for doing so, we will increase a little bit the amplification, because we want to see the PN junctions that are not present, or that cannot be seen at the moment, especially here in the parts on the bottom left-hand side. They tend to appear with rising temperature. So let's increase the temperature, and 90 degrees is a nice value, and the image should now you will now, with rising temperature, see the PN junctions of the other parts of the operational amplifier getting more and more clearer. It takes some time. If yeah, you see now starting from on the bottom part, signals getting clearer. It takes a little bit of time. The sample is on top of a carbon tape. The carbon tape is insulating, so it might take some time until the temperature gets there. But you now see it's becoming more and more defined. You see the wells very clear now, also EBIC spots. Yeah, we can also have a quick look at the graphics. Yeah. The graphics show now we are just below the set point of 90 degrees Celsius. We're at 70 degrees centigrade. And you already see now that all the PN junctions and wells are becoming very clearly seen, and you clearly see the temperature effect on the PN junctions. Now, before we end this session, we will do a nice analysis, and let's decrease again the brightness and the contrast, and use the save image to grab both images, EBIC and SE image, simultaneously, and they are automatically transferred to the EBIC overlay tool, and we can do further quantitative and other analysis. So make a little bit nicer image, a little bit slow scan. So now I'm just press the save image button. Now both images are grabbed simultaneously and passed to the EBIC overlay tool, which will start soon. Yeah, now here we have it. So this is the current image in color. We have different color scales. For example, the red scale is going from black to red. Temperature is from blue to red. This is often used for EBIC because you can visualize currents flowing to the amplifier and flowing from the amplifier very clearly. You see the blue spots here in the EBIC amplifier, in the EBIC image. They are from the PN junctions, electrons flowing from the amplifier, and the red ones are flowing to the amplifier. You can make a quantitative analysis by moving the line over the contacts you want to measure, and on the bottom you see the measured current. All the parameters are stored together with the image, so you always have the EBIC parameters together with the image, and you can do the further analysis, quantitative analysis, also offline later. Now the SE image, the corresponding SE image is here, and if we do an overlay, you see now this is the EBIC image, but if you change the transparency, you immediately see where these PN junctions are located. Now, for EBAC, for example, you would prefer a simpler curve, so just from black to red, where you can increase the contrast such that only these parts can be seen that you want to see afterwards. And if you now go to the overlay tool, you clearly see these structures along with the SE image. And by defining a threshold, you can suppress different color grades, also grayscales. There's one more interesting or often used color table. It's the rainbow color. This is used to distinguish very slight changes in currents or also resistances. So we have image like that, and you see here the scale, so you can distinguish now between 1 and 2 microamps, but it's also valid for currents as low as some picoamps only. The EBIC amplifier has a resolution of some tens of femtoamps, so you can also use it for very, very small currents. Now the overlay image again, you can overlay to change the transparency and use it for further analysis. And of course, store every image just by pressing one button. So with this analysis, we finished the live demo, and I pass over to Andrew.
All right, thank you, Andreas. That was very interesting. We've come to the end of our workshop. I'll just switch back to my slides, of which there are not many. So we're here, and all that's left is for me to thank you for your attention and ask you to pose any questions you may have. Please just post them in the chat, and we'll be happy to address them. Otherwise, feel free to just leave whenever you're ready. And again, I thank you, and I hope to meet you somewhere at a meeting or conference soon, or at the next online event. Have a nice day. So we do have some questions. Let me read them out to you. So, what is the difference between GND and EBIC GND in the routing tab? There's ground and there's EBIC ground. What's the difference?
Yeah, in principle, it's the same ground, but we have a separate line for grounding the probe tip that is connected to the EB amplifier in order to have as less noise as possible.
All right. And another question from Jose is it possible to perform usual stage tilting at FIBSEM? Yes, it is, provided there's no other add-ons to your fib that consume the right-hand side of the chamber where the stage is supposed to go. Tilting to fib angle is no problem.